Good morning, calculus students and enthusiasts all around the world, and welcome to day 5 of our AP Calculus free response question advent calendar. Let's go ahead and find the 5th slot on the chocolate advent calendar, and then of course we can do some math. Ooh, I just found it. It's over here on the left. Let's zoom in to that. It's here by the door with the bird. Looks like we've got maybe a blue truffle then behind the door today. I'll put today's free response question on screen now while I get into this chocolate. Today we will be doing a integration problem, right? We got some areas, we got some volumes. Should be a lot of fun. Oh man, look at that. It's green behind the door, a green chocolate. And again, it is a sphere. It's all roly-poly rolling around. Let's get in here and see how this chocolate is. These chocolates are so good. I wonder how many calories are in each one over the course of this month. I'm probably going to approach the weight of an adolescent elephant. That is a very standard chocolate. Very good. Very good as usual. All right, let's go ahead and do a little bit of calculus. This is problem 1 from the 2002 AP Calc AB Exam. This is part of the graphing calculator section, so we will be using a graphing calculator throughout this problem. Let's read it. Let f and g be the functions given by f of x equals e to the x and g of x equals lnx. I'm going to refer to lnx as log x, if that's okay with you. Part A is to find the area of the region enclosed by the graphs of f and g, e to the x and log x, between x equals a half and x equals 1. So we need to integrate the difference of the functions from 1/2 to 1. That's how you find the area between curves. You may want to sketch these functions. E to the 0 is 1, and from there it grows exponentially. And as x gets very negative, e to the x approaches 0. On the other hand, log x, for values of x that are very close to 0, log x is very big and very negative. And then as x gets larger, log x grows indefinitely, although it does it very slowly, and is certainly less than e to the x. And remember, we want to find the area between x equals 1/2 and x equals 1. So maybe that's right around here. This is x equals 1/2. And then x equals 1 is going to be right here. And we know that x equals 1 is where log x intersects the x-axis because log 1 is 0. All right, so we can see that log is the lower function and e to the x is the upper function. So for our integral, we're going to integrate from 1/2 to 1, that's given, and we're going to integrate the upper function, e to the x, minus the lower function, log x. This is going to give us the area of that region. And we can use our graphing calculator to figure this out. So I'll open up the graphing calculator, press the math button to get access to all these functions, and I'm going to use the integration function. We're integrating from 1/2 or 0.5 up to 1, and the thing we're integrating is e to the x minus log x. And then of course we're integrating this with respect to x, and we can enter this to get our answer about 1.22. So that is the area of this region. All right, let's move on to part B. Find the volume of the solid generated when the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1, that's this region here, which we just found the area of. We want to find the volume of the solid generated when that region is revolved about the line y equals 4. So that's a line that's up here, which is above this region. And we're going to revolve the region about that horizontal line, and we need to find the resulting solid. Now, hopefully you can picture if we revolve this region about that line y equals 4, you can see that it is the green curve, which is log x, which will be tracing the exterior of this surface. The interior is going to kind of be carved out by e to the x. And so this is what we call a washer problem. To find the volume of this solid of revolution, we need to integrate or add up the areas of all of these washers. So what are we going to do for part B? Well, again, we need an integral from 1/2 to 1. And what we're integrating is the areas of these washers. We can find those areas by taking the areas of the outer circle, which is traced by log x, and subtract the area of those inner circles, which is traced out by e to the x. Now, the area of the bigger circles will of course be pi r squared, and r, the radius of this bigger circle, which is traced out by revolving log x about the line y equals 4, the radius of that circle is this distance here. And that distance is just 4 minus log x. I just redrew it a little more nicely. Once more, the radius of those bigger circles is the distance from y equals 4 to that lower function, and that is 4 minus log x. As for the smaller inner circles, the radius of those is the distance from y equals 4 to that upper function, and that is e to the x. That distance is 4 minus e to the x. Those are our smaller radiuses of the inner circles, which are actually being carved out of this solid. Okay, so coming over to set up our integral. Both of these areas have a factor of pi in them, so we'll just take the pi out of the integral. The radius squared for the larger circles is going to be 4 minus ln x squared. And then we're subtracting the areas of those smaller inner circles, which is 4 minus e to the x squared. We're integrating this with respect to x, and we can just calculate this on our graphing calculator. So on the calculator, again, I press the math button to access these functions. Press the integration function. We're integrating from 1/2 up to 1. What we are integrating is the difference of the squares of the radii. We'll multiply by pi after the fact, so let me enter in these radii squared. So there's the difference of the squares of the radii. We're integrating this with respect to x, and there is our answer, about 7.52. But don't forget, we need to multiply this by pi. So finally, the volume of this solid is about 23.61. Finally, moving on to part C. Let h be the function given by h of x equals f of x minus g of x, so just the difference of e and log. Find the absolute minimum value of h of x on the closed interval from 1/2 to 1, and find the absolute maximum value of h of x on the closed interval from 1/2 to 1, and show the analysis that leads to our answers. Okay. To find maximums and minimums, of course, we're going to need to take the derivative of h. That way we can find any critical points. We also know that we're going to have to check the endpoints, because remember, this is defined on a closed interval between 1/2 and 1. So this is sometimes called the candidates test. What are the candidates for the extreme values? Well, those would be the endpoints, 1/2 and 1. So we will need to check those, and then also the critical points. But to find the critical points, we have to take the derivative. So let's just jot this down. What do we need to check? Well, we'll have to check 1/2 and 1. And by check them, I mean we need to plug them into the function h of x and see what those values are in order to establish minimums and maximums. And then we'll also have to find any critical points and check those. So let's find h prime of x, and then we'll be able to find the critical points. Now remember, h of x is just f of x minus g of x, which is e to the x minus log x. So h prime of x is just f prime minus g prime. F prime is e to the x, because the derivative of e to the x is e to the x. And then we subtract g prime. G is log x, so g prime is 1 over x. All right, so what are the critical points? Well, the critical points are where this derivative doesn't exist. It doesn't exist at x equals 0, but 0 is not in this interval, so that doesn't matter. And also where the derivative is equal to 0. So let's set this derivative equal to 0, and then we can use our graphing calculator in order to solve that. So I'm going to enter this function, e to the x minus 1 over x, into my calculator. And then we can look at the graph. Pressing the graph button, we see a function that looks like this, and we need to see where does it pass 0 in our interval. And that would be right about here. Let's see if we can get the calculator to give us this number. It appears to be about 0.567. That's when y is 0, when x is about 0.567. So I'll write that over here. That is our critical point. So we need to check x equals 1/2, x equals 1, and our newly discovered critical point at x equals 0.567. We need to plug all three of these values into the function h of x and see which is the maximum and which is the minimum. Plugging them in, these are the values we get. And we can see the lowest value is at that critical point where x was about 0.567. Here, the value of h is about 2.33. So that would be our minimum. And the maximum we see is at x equals 1, where h takes on a value of 2.72. And remember, these were discovered on a closed interval. So on that closed interval, this is actually an absolute maximum and an absolute minimum. And that completes our solution to free response question 1 from the 2002 AP Calc AB exam. Let me know in the comments if you have any questions, and if you find these AP Calculus videos helpful, please consider supporting Wrath of Math as a channel member to help me create more high-quality calculus content and to get access to exclusive calculus videos. I'll see you tomorrow for the next episode of our AP Calculus free response question Advent calendar. Thanks for watching.